Alright, so this is a great little example. What we have here is a disk P, which has a given mass, and we're told that it's able to slide down a smooth horizontal surface. A rubber band having a given stiffness and an unstretched length attaches B to a fixed peg at O. We're told that disk P is set in motion initially with a speed of Vp1 in the direction shown with a given value of r. Based on this given information, we're asked to determine the polar coordinates of the velocity of P when P is a different distance away from point O. So the first thing I want to do is I want something very simple. I want to draw a free body diagram for the system from the top view. And if we do that, I want you to note that the only force that can really exist on the system in that plane is the force due to the spring, which I can call F sub spring. And of course, this is going to point through the point O. And so as a net result of this, the sum of moments about point O is going to equal 0. Now this is a pretty positive indicator that we're going to want to use conservation of angular momentum here, and that's certainly the case. So I'm going to start by saying that h about O at state 1, that is the initial configuration, has to equal h about O at state 2. And so if I compute this quantity, h about O at state 1 is of course going to be r1 across the mass of the particle times v1. And if I do some substitution here, this is going to give me, using the unit vectors given in the problem, r1 in the E sub r across the mass of the puck times the velocity initially, which is Vp1 times, I'm going to go ahead and call this angle here to be theta, so it'll be cosine of the angle theta in the E sub r, plus Vp1 times the sine of the angle theta in the E sub theta. So if we go ahead and work out that cross product, E sub r cross E sub r is 0, E sub r cross E sub theta is k, so I'll have back here m times r1 times Vp1 times the sine of the angle theta in the k. Now the next thing I'm going to do is keep in mind what I'm asked for in the problem, the polar coordinates of velocity at the second state. So I'm going to go ahead and compute h about O now at that lighter state. So in this case this is going to be r2 cross m times v2. Now if I do the substitution here, I'll now have a distance r2 in the E sub r. I'm going to cross that again with the mass of the particle. But now what I'm going to have is the velocity of the particle in the r direction in the E sub r, plus in this case the velocity of the particle at state 2 in the theta direction in the E sub theta. Now if we work this out, what we're going to realize here, E sub r cross r goes to 0, E sub r cross E sub theta goes to k. So what I'm only going to be able to extract here is the theta component of the velocity. And this is very important. What this means is that our solution's not complete yet. So if I go ahead and equate the initial and final angular momentum, what I have is that mr1 times vp1 times the sine of the angle theta in the k is going to equal m times r2 times v2 times theta in the k. We can note at this juncture that the mass will cancel out from both sides, as will the k unit vector. And so what we'll get back is that v2 theta is going to equal r1 divided by r2 times vp1 times the sine of the angle theta. Now if we look at this carefully, again we've only computed the theta component of the velocity of the second state, so we have to turn to something else. That something else, because we're looking at a change in position, is going to be the work energy equation. And so what I can say here is that T1 plus V1 plus the non-conservative work done moving from state 1 to state 2 has to equal T2 plus V2. Now T1 is a relatively straightforward component. This is simply going to be 1/2 times the mass of the puck times Vp1 squared. V1, if we go back to the problem statement, we can see that this is an elastic band, not a true spring, and that the initial value of r is actually less than the unstretched length, and so actually we have no elastic potential at state 1. And so V1 is simply going to be 0. Again, keep in mind that elastic band can't be in compression, which makes this true. You'll note that we have no forces which are non-conservative in nature here, so that U1 to 2 non-conservative is going to end up being 0. At the final state, we're going to have a kinetic energy given by 1/2 m times the final speed squared. If we refer back to above, this being the total velocity of the particle at the second state, that tells us that the total speed squared is going to be v2r quantity squared plus v2 theta quantity squared, where we already have determined v2 theta. And finally, v2 is going to be 1/2 times k times the amount of stretch in the spring which in this case is going to be R2 minus the unstretched length R0 quantity squared. So if we go ahead and substitute these 5 terms back into the work energy expression, what I'll have is that 1/2 times m times Vp1 squared is going to equal 1/2 times m times V2r squared plus 1/2 times m times V2 theta squared plus 1/2 times k times quantity R2 minus R0 quantity squared. If one looks at this carefully, what you realize is that the only unknown in this statement is V2r, and once we have that, we can write down the velocity at state 2 in polar coordinates is simply being V2r in the e sub r direction plus V2 theta in the e sub theta. From here, it's a relatively straightforward numerical exercise, so I'll leave it up to you to do. Best of luck, everyone.